the second example. If you're here, you're probably wanting to know some more specific details. So let's take a look at example 2. The Spaceshot is an amusement park ride that gently raises riders up a tower and then rapidly bounces them down using compressed air. The velocity, it sounds nauseating actually. The velocity of the Spaceshot for 0 is less than or equal to t, which is less than or equal to 14, is modeled by a piecewise linear function shown in the figure below, actually to the right and below, where t is measured in seconds and v is measured in feet per second. All right, let's take a look at each one of these individual parts. At what times in the interval between 0 and 14, if any, does the Spaceshot change directions? And give a reason for your answer. Part B. At what time in the interval between 0 and 14 is the Spaceshot the highest, and how high is the ride at that time? Part C. Find the total distance the Spaceshot travels during the time interval from 0 to 14. And then finally, number 14, write expressions for the velocities, the ride's acceleration, the acceleration function, the velocity function, the distance function from the ground that are valid for the time interval from 10 to 12. So that one little line segment that's in the little picture. Okay, boom. Calculator inactive, so we don't get to use it on this one. It's okay. We do have a picture of a graph. And remember, as far as these problems go, why is this graph way the heck down here? I don't know. As far as these problems go, they can ask these contextual problems either with equations, with graphs like you can see it like this, or sometimes it's table of values, and you're going to see that probably in the next question. At what time in the interval between 0 and 14, if any, does the Spaceshot change directions? Well, it's going to change directions when the velocity changes signs. This is going to be so easy to find. When it changes from positive, negative, negative, positive, it's just like finding mins and maxes. So we can see one's here at 8, one's at 6, one's at 8, and one's at 14. Don't include the endpoints, of course. And we're going to write the Spaceshot. Go ahead and insert any vomiting emoji that you want to right here. Changes direction at t equals 6, 8, and 10 because v of t changes signs at these times. And we're done with that part. That was so easy. We just got 1 or 2 points, I don't know, for this particular free response question. At what time, part B, in the interval between 0 and 14 is the Spaceshot highest, and how high is that? So this means one and only one. Water. Okay, this means one and only one test, and that test is the closed interval, otherwise known as candidates test. And those candidates are where our position. So we want the position function. So it's like the position function's derivative, which is v of t, is equal to 0, so is our critical numbers, and then also our endpoints. That's what we've got to check. Okay, so we already have all of the points at which it changes directions, where our critical points were. That's basically part A of this thing. Now, can I eliminate any of them, though? Let's look over here, back at the graph. Back at the graph, we've got this first one at 6, it changes from plus to minus. Change from positive to minus, that's increasing to decreasing, so this one here is a max, so we're in good shape with that one. But over here at 8, it changes from negative to positive. That goes from decreasing to increasing. This one is a relative minimum. So that one we can go ahead and eliminate. And then over here at 10, it changes from positive to negative again, which means another relative max. So we basically only have to check these two against the position at each one of the endpoints. to see which one is the highest. Which one do you have a feeling for? What do you think? It's not 8. Okay, so what I'm going to do is list out my critical numbers. Critical numbers, boop, 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 where v, and you probably want to write this down, so where v of t is equal to 0, that's sometimes worth a point where you write that down someplace. It's on your page someplace. This happens at t is equal to 6, 8, and 10, just like it was in the previous question. And I am going to eliminate this one because that one is a relative minimum, and that's going to lessen the amount of work that we have to do. Okay, so let's kind of write ourselves an equation that we're going to do the closed interval test on, because that's what you need. You need an equation so you can take its derivative, find the critical numbers, and we know that the equation that we're looking for is our position equation. So our position equation we're going to get, excuse me, we're going to get from our velocity function, which we will take the antiderivative of, like so, in order to get position, as we've done. And we need some bounds of integration on this one. Well, I think in here someplace it says that it starts on the ground. I'm going to assume that it starts on the ground. I think it said it in here someplace because, hey, how else are everybody going to get on the ground, get onto the ride unless it starts on the ground? So it's going to start on the ground and then go up to some x value here. So from 0 to x gives us s of x minus s of 0, which is 0, which just means our position, our height function, I guess, is equal to 0 plus our definite integral from 0 to x of v of t dt. So here's our height function. And we take its derivative. Whoops. Take its derivative, and I'm taking the derivative of a definite integral function. So they cancel each other out with a change of variables. I just get this v of x here. I set that thing, I'm going to set this thing equal to 0. So s prime of x, which is equal to v of x, which is equal to 0. This is exactly what we said right up here, and we have our critical numbers. Okay, so to carry out the justification of this and the actual closed interval test, we just usually make ourselves a table of values. So we've got x, and we have our position at that particular time, and we want to have our endpoints 6, skip 8, we didn't care about it, go to 10, and 14 I think was the last one. So we're going to say that it starts here on the ground, and then as far as it goes, we need to plug each of these things back in to our position function, which means that we're going to have to take a definite integral here of the velocity function. And since I don't have an actual function to do that with, I have to use the area on the graph that was given to us in this particular problem. So I'm going to clean this graph up a little bit so I can write on it and color it and stuff. Okay, so for 6, this is the way it's going to look. Go away. It is the definite integral from 0 to 6 of v of t. Oh yeah, it was t, yes, dt. Okay. So I want the area from 0 to 6. Boop, boop. Equals. So let's take a look at that. Maybe I color this part in pink here. It's just a trapezoid. We want to find the area of this trapezoid. So if you have forgotten, the area of any given trapezoid is equal to 1/2 base 1 plus base 2 times the height. Our two bases, that's the top and the bottom of this because they're parallel. I can see that the bottom here is 6 and the top is 4. So let's see, 1, 2, 3, 4. Yeah. So for the area for this one, I have 1/2 of 6 plus 4 times my height, and my height is 20, I can see here. It's 20. And that's a 10. I'm just going to take half of this and get a 10. 10 times 10 is 100. So we got 100 there. There we go. So it just went up to 100 feet. Why did I write that in pink? Should have been in blue. All right, there's the first one. And now we can skip the next one, except for we need it whenever we go to do the one at 10 because we're going to be taking some area away from it. Right, so our definite integral that we're going to set up in order to find the value at 10 is from 0 to 10 v of t dt. So we know that we have 100 from before. We're going to subtract something off, which is this pointy triangle that's right here. I'll change the color. No. Change the color. There we go. And then find the area of a triangle. Easy. Do it in green here. It's 1/2 of the base. My base is 2 here. Times my height, 20, 40, 60. Times the height is 60. So that just is 60. But remember, this is a negative 60 because it's down below the x-axis. So I'm going to subtract 60 here. And so you can see that's the reason why we eliminated the 8, because we were at 100. We just took 60 away from it. It was a relative minimum. Right? And now we want to add back in this triangle from 8 to 10. You can see it's going to be smaller than what we had. It's not going to be as high as where we went the first time because we're not going to add in as much as we just took away. All right, so to find its area, 1/2 of its base is 2. And its height this time only goes up to 40. So the 2 and the half cancel, and I have a positive 40 for the area on that one. So plus 40, which means I overall just lost 20, so that's going to put us at a height of 80. All right, so far we got a clear winner. All right, and then we're going to have to just formally compare it to what we have at 14. It's definitely not going to be 14 because you can see we're losing some more area here. Oh yeah, I need to write this thing up here. So definite integral from 0 to 14 of v of t dt. So I will have the 80 that we had before, but we're about to subtract something because we're down below. This is just like formality here. But I need to actually check this. Okay. Another triangle, its base length, let's see, is 4, and then it's going downwards 40. So its area is 1/2, that's a half, 4 times 40, which is 80. So we went down 80 here. Oops. Whoa, 80 minus 80 is 0. Well, does that make sense? We should be back at the ground by the time the ride's over. Could you imagine it stopped like 15 feet above the ground? Oh, okay. You guys need to jump down or something. All right, we got a clear winner. If I did have to justify this, I definitely, like, every bit of work here is part of the justification. This is the closed interval test. So we're going to say the Spaceshot reaches its highest, or reaches a height, I guess. Its highest height? Whatever. Reaches its maximum height, that's a better word, of 100 feet at t equals 6 somethings, pretty sure it was seconds. There's the conclusion on that. What are we, like halfway done? Halfway done. Find the total distance the Spaceshot travels during this time interval. Okay, no problem. Let me move my graph up a little bit. So total distance, as we've talked about before, and I think it's one of the facts. Let me make you completely dizzy here by scrolling back up here. Yeah, there it is right there. Total distance, bam. It's the definite integral over your interval of your speed function, your absolute value of your velocity. Okay, let's make you dizzy again. Hey, we are on a Spaceshot ride anyway, which just means this. So we want to find the total distance is the definite integral from 0 to 14 of the absolute value of v of t dt. Close those. Now, what the absolute value does to our graph is it just reflects anything that's down below up above the x-axis. So this point that's down below at negative 60 is going to go up here to positive 60. So it's now up here. And then this point that's down here, 12, negative 40, is going to go up here to positive 40. And then we have that part of the graph there. All right, and so now we want the areas of all of these pieces, which we've already done. We just have to switch some of the signs. So it's area of all that, all this, plus this, and this one over here. And like I said, pretty certain we found that one as 100. We found this one as, it was originally like negative 60, so this one is positive 60. This one was 40. Double check, just to be sure. Yeah, 40, and then an 80. Okay, so we just want to add up all these numbers. We got 100 plus 60 plus 40 plus 80. So that's another 100. So that's 200. Plus 80 more is 280 total feet. And that's how far it's traveled in totality. Lastly, all right, here's the tricky one, I think. Write expressions for the ride's acceleration, velocity, and distance from the ground that are valid for the time interval from 10 to 12. So going back up here to this picture, we want only this part here. So there's the velocity function. You can see it's linear. So to find that velocity one, it's going to be a piece of cake. We just find the equation of a line. Well, if you take its derivative, you would have its slope, and the slope of that thing tells you your acceleration function. So that's actually what I'm going to start with. So the acceleration function is equal to the derivative. What is this? What's going on? The derivative of the velocity function, and then since it's a line, it is just a slope. It's just the slope of that line. So we're just going to find, this is an algebra 1 kind of problem. Honestly, I've got, let's see, my y values are a negative 40 minus 0 over 12 minus 10, negative 40 over 2, I got a negative 20 is my slope. So there's my a of t function. It's just negative 20, a constant acceleration. Okay, and now to get the velocity function, it's just the equation of that line. Now I'm going to do the equation of this line kind of in point slope form. And I got a couple of points that I could use, and the point that I'm going to use is I need to come back up here. I need a point, let's say, that's actually on this graph. And that one was, no, it's not the point that's on the graph, because it's a point that's on this graph. It's this velocity function here, which sure, it doesn't, I don't get to actually use those 2 points, because there's no equal sign on this, on each one of these inequalities. But I'm going to use those points because that's where it would touch, okay? So my velocity function, I'm going to do this in point slope form using the point, let's say 10, 0, right? So this is velocity, which is like my y, minus 0, which is like nothing, is equal to my slope, which we just found is negative 20, times my t value, minus my initial condition, which was, what did we say, 10. So minus 10. Which means our velocity function is just simply equal to negative 20 t plus 200 whenever we would distribute that through. Right, and this might make sense. We'd have a negative 20 slope, and if we continued this line, it would hit someplace up there at 200. Okay, we're part of the way there, almost done. Now we just need to find the position function. To get the position function, I'm going to take the velocity function and take its integral. So I'm going to get back to the blue color. the antiderivative of v of t dt should be equal to the s of t. So my velocity function we just found, negative 20t plus 200 dt, should be equal to be negative 20t squared over 2, which makes a negative 10 t squared, plus 200t, and then plus c. Do not forget your constant of integration. And then I'm going to say one of the tougher parts of this is trying to figure out how do I find that, that c value. And I'm going to find that c value, this is what I wanted to do before, by looking at the position that we came up with at, laser pointer, that's what I'll do, at 10. At 10, it is 10 comma 80. Yes, again, just like we talked about before, it doesn't actually hit at 10. However, I mean, the 10 is not valid for this particular equation, but that's where it's going to start whenever it does this particular interval. So we're still going to use it in order to find what that c value is. So we have this initial condition. I plug in 10, and I'm going to get out 80, did we say? I think. Double check. Okay, yeah, we did. Okay. Which means I'm going to take a negative 10 times 10 squared plus 200 times 10 plus c is supposed to be equal to, didn't close those parentheses, 80. And now I just have to solve that for t. It should be a piece of cake. So 10 squared is 100. 100 times 10 is 1,000. So I've got a negative 1,000. Plus 10 times 200 is 2,000. Plus c is equal to 80. So combining those, I got 1,000. Plus c is equal to 80. And now subtract over your 1,000, and you get negative 920. There we go. So wrapping this up, our position function is equal to negative 10t squared plus 200, no, come on, 200t minus 920, and we're going to call it right there. All right, then that concludes that particular free response question involving a graph instead of an equation. Let's take a look and see what's next for you. So just like before, I'm going to suggest that you take about 15 minutes and work through this problem. And notice that this problem is going to give us, instead of an equation, a table of values. All right. And then you have the option of either checking your answers with an answer key on my website or joining me in the next video where we go through it step by step.